This presentation relates to the configuration of the PIX ASA devices. It's part of the Cisco Certified Security Professional or CCSP certification. And basically we're moving from a certain range of certifications towards a newer set. Much of the material which was covered in the old certification modules has actually been refocused and placed within a much more structured approach to the certification subjects. So the PIX device certification has moved from securing networks with PIX ASA towards the new one, which relates to this one, and that's securing networks with the ASA Foundation. We'll see that some of the CLI configuration is now being replaced by with a graphical user interface. But much of the certification that was contained within the other certifications has now been placed within a range of these modules. Network Sims contains a wide range of certification challenges, including Cisco Academy Network Security 1 and the PIX SNAPA exam, and a full range of ASA challenges. So if we take a look at some of the challenges here, we see that we have Cisco PIX challenges using both version 6 and version 7, and then that moves on to ASA challenges, which are more advanced in their scope. Okay, so let's look at the PIX ASA firewall. The ASA PIX devices have a wide range of applications. This includes setting up simple firewall rules, using access lists and access groups to be able to block or permit traffic. A key feature of the PIX ASA is that it's typically defined as a closed firewall, in that traffic is only trusted from a high-level interface to a lower-level one. And if we want traffic to flow from low to high, then we must configure this. It also does URL filtering, where we can actually filter at the application layer, and also port blocking. It also defines a cut-through proxy, where we can authenticate users onto a system to allow them to be able to be authenticated to use certain services such as HTTP, Telnet and FTP. It implements intrusion detection systems, especially with an inline IDS, and then we can implement an IPS system using the IDS. We can implement shunning, where shunning allows us to thwart a short-term threat, but when we reboot the device, the actual blocked ports become available again. It supports encryption, especially towards IPsec and tunneling, and it now supports a web VPN using an SSL type connection. This has the advantage of being able to use encryption through a web interface. And as firewalls are typically a single point of failure, we have enhanced failover, so that when one PIX ASA crashes, then another one will be able to detect it and take over its place. Some of the devices that we have for a small office, we have the PIX 501, which is a fairly limited device with only 2 interfaces and up to 7,500 connections. The PIX 506 raises this to 25,000 connections, and again only has 2 connections in and out. For a medium-sized office, we have the PIX 515E, which can support up to 130,000 connections and can have 6 physical interfaces. For this we can have 2 licenses for it, a restricted. The restricted doesn't allow us to have failover or VPN acceleration, where an unrestricted license allows us integrated accelerator, failover support, more LAN connections and also VPN acceleration. Then we have the PIX 525, which goes up to 280,000 connections and is used on an enterprise type network, and then on to the PIX 535, which has a 1 GHz processor, 1 GB of RAM, and can support up to 500,000 connections. Cisco are now phasing these PIX devices out towards the new range of devices, which is the ASA. The ASA 5520, for example, has integrated VPN, SSL VPN, 8 interfaces, supports PIX 7 and PIX 8 iOS. The basic architecture that we have is that we have various zones that we define, and we typically have with 3, a trusted, a DMZ and an untrusted. Each is given a certain security level. The higher the security level, the higher the security of that zone. So in this case we define 100 as the highest, 50 as the next highest, and then 0 as the lowest. By default, traffic cannot flow from a lower security level to a higher one, but traffic is allowed from a high to a low. So in this case, traffic is allowed to flow from trusted to DMZ and from trusted to the untrusted. The PIX itself understands the traffic and will open up the firewall so that the traffic can flow back. But the key thing is that the traffic originates from the trusted network here. Traffic is also allowed to flow from the DMZ to the untrusted and back again, because the firewall will open up the port. But if we want users to be able to access devices from inside the DMZ, we must open up some conduit, some path to allow access to it. The PIX ASA device typically supports a network address translation, and with this we define a global pool, and the global pool are the addresses which are used outside the network, and then we can have a mapping from our global pool into a local pool. So in this case, these hosts, or this host, is accessed from outside through its global address. So in this case, our NAT mapping is from this address, from outside, into this address. The same can happen with our trusted, that we can have a private address space and then these map on to a global address space. The PIX-SA can be configured either through the command line interface or from ASDM. So in this case we see a screenshot of the ASDM interface. And with this, the main screen, we see what interfaces that we have. So in this case the ASA has 3 main interfaces, and then there is also an Ethernet management interface. The addresses of each of the interfaces is defined here, whether the line is up and the protocol is up. We also see things to do with the CPU, memory, the traffic status, and so on. We should also be able to see the version of the iOS that we have, the device type, and so on from this screen. And then from the license, we can view the license inside this tab here, and we can see here there are 4 interfaces. It's a base license. We can have 50 VPN peers. If we have a look at the actual ASA interface, this is the license, there's the general information. We can either go to the configuration mode, and it's here that we configure all the interfaces and the protocols, or we can go to monitoring mode, and from here we can actually look at various things like VPN connections, routing tables, and so on. For the command line interface, to be able to configure the PIX ASA, we can use PIX6. PIX6 is still available on many networks, and the big difference between PIX6 and PIX7 is that this is a fairly flat configuration structure, where PIX7 ASA 8 has a more hierarchical approach. So in this case we define the host name, define the domain name, go into the interface and apply the IP address. Inside the ASDM we can do the same thing. We can define its name, its security level, and its IP address. We can change here, define its subnet mask, its MTU, and so on. There are various other parameters that we can define, such as duplex, speed, and media type. It also shows us what our MAC address is of the actual port. For our host name, we can go to our configuration, and then we have our device management. Then under device we can actually set the host name and then also the domain name here from this device administration and then device. Then for our interfaces and CLI, we can use the nameif to give it a name. We then define the security level and then give it a no shutdown. So the equivalent of this would be in the interfaces. Again, this defines the name that we would give it. This is the security level IP address, or we can define it through DHCP. And this shows another example. We give each interface a name. If we want to shut the port down, then we create a shutdown command. This option here allows us to enable the interface or to shut it down. This will shut down, this will enable it. Okay, so this shows the basic configuration. So in this case we have Ethernet 01. We can then enable the interface here. We can define it as management if we want, and then we can define its name, its security level, its IP address, and then we can configure any other hardware properties from it. We can also define some banners so that when users or administrators log in, they will get either a message of the day, a login message, or an EXE. When they change into the executive mode, they will also get a message. So from the actual configuration screen, just quit here, and then back into device administration, and then it is here we can actually define our message if we want, and we can even use the name of the host or the domain name as required. And then once we're happy with that, we can then apply. We can also go to our device at any time and have a look at the actual configuration. So we can see in this case the interfaces have been defined, security level 50, 100 and 0 here. And then we can see that we have a web server enabled. We allow telnet, SSH and so on. A key thing that we must do is that we must set the root. We must set roots for the PIX ASA device. This is key as the PIX does not actually learn new routes. It will listen to routing updates, but it will not update its routing table automatically. This is to increase the security level. So in this case, we apply a route for data packets which begin with 10.0. So when this part matches, then the PIX ASA will send those data packets to this port. And we can do the same with our device by selecting routing, and then we set up a static route such as this one. And then we add, and we can define on which interface that we're dealing with, the IP address, the mask, and the gateway. We can give it a metric level so that when it's added into the routing table, the PIX ASA will decide which has the lowest metric to be used. So we can see here an example. So we have actually defined that anything that comes in with this address will be sent to this port with a metric of 1. So this port is here. So anything coming in to the PIX with the address 10.0 will then be sent on to this port, and hopefully this perimeter gateway will then know where to actually send the data packets on. So in this case, we've configured the Ethernet 0 port to have this address. Ethernet 1 has the highest security level and it has this IP address, and then Ethernet 2 has a security level of 50 and has this address. When we look at the routing table on the device, we can see here that we can have the directly connected interfaces that are automatically added to the routing table, and then it is also added the static route. We can see this in this example when we look at monitoring our routes. So what we see is the interface name, the IP address, and whether they're connected or whether they're static. So let's look at adding another route. So in this case, we're adding it on the inside interface, and anything with 172.10, which is this network here, 176.10.1, will be sent to this port. So if a data packet comes in with 176.10.1.2, say, then it will be sent to this port, which will then send it on to this port. As this network is directly connected to the PIX, it should know to send it on to this port to be able to connect to this device. And now we can see that the routing table has been added to, so that 176.10.1 is then sent to 192.168.11.3. In this case, this should be 2.3. We can see this again in the ASDM So we take from inside, anything with this address is sent to that IP address, and we see here that that is then added as a static route here. The other route that we typically set up is for any other data packet with an address that we don't actually know how to route, then it will be sent to the default gateway. So as a default, any other IP address will be sent to this port here. So any data packets, say for outside, will be sent on to this interface and will be routed out. Some of the protocols that we have need to be fixed up. These are especially related to the ones which set up server ports on clients. In this case, the PIX-ASA must understand their operation and then open up the firewall port to allow the connection to happen. So typical difficult protocols are FTP and RSH. SIP also creates certain problems. So if the protocols that we have map to different ports, we can use the fixup protocol command to actually define which ports these difficult protocols relate to. The PIX-ASA typically deals with network address translation, where we have a public IP address space, and then behind our firewall we can actually have a private address space. Network address translation allows us to map addresses inside to ones outside. So in this case we set up a global pool. The global pool relate to the addresses which are seen outside, and then these then map to our inside and DMZ addresses. So in this case the hosts for this pool 1 is defined with these two. These will be the addresses which are assigned inside. So for example, the first address could be assigned here, a second one, third one, and fifth one could be assigned for this node. And then these are then mapped into a global address space. So for example, if this port interface was assigned first, it might be given this address. So anyone accessing this from outside would use 10.1.1.2. Then in our DMZ we have a different mapping because we have a different range in here. So the addresses 172.10.10 are mapped to outside as 110.1.1.201 up to 254. So this port here could be mapped to this address here. So this is done dynamically. When an address is required, it will take one from the pool. To configure it with inside ASTM, we can see here that we have dynamic NAT, not static. This is done dynamically. This is the source address with inside our network, and these are the range of addresses which are to be mapped from outside, on the outside interface, to any destination. So if we look at our ASTM, and here are our interfaces, so we have test 3, which is inside at 4.0, and then we look at our NAT, and we'll add new NAT, so using the dynamic. So our source in this case is test 3, then we can define 192.168.4.0, define our subnet mask as that. Just check our NAT options, everything's fine there, and we want to map that on to our outside interface, test1, and then we can define our global address, and we're putting it on to the test1 outside interface. And so for this we can then define what the addresses will be on our outside interface. So we can define 10.1.1.2 to 10.1.1.200, and then we can define our subnet mask, and we define our pool ID. So then we have our mapping. So these addresses are then mapped to these addresses outside. As we can see here, this is how it's viewed. Remember, dynamic NAT will actually allocate the addresses as required. A good way to preserve addresses is to use port address translation. Be able to allow our servers and our forward-facing devices to be accessed from outside, we typically create a static mapping between the outside and one of the inside networks, typically inside the DMZ. So with this we create a static mapping, and the way that we view it is like this. This says take the host in the DMZ, this one here, and map it to 10.1.1.201. So from outside, this node here has this IP address. The same again, inside is this address. So the 1.5, if we define that as 1.5, will be viewed from outside as 10.1.1.202. So this host will be viewed at this address. Same again, we can actually define our static map, NAT, and we define what the source address is and then what the translated address is. And we can see the mapping here. We can see here an example of the configuration. So using NAT, this is the address on the inside, and it's translated to the outside interface. This is the address for outside.